Different things we can do in Haskell, but before we do that, best time to ask questions or make comments is when you have it, so please don't wait till the end. If you do have a question, please do draw my attention. If you raise your hand, I may not notice you. You may think I'm ignoring you, but I'm not. Do draw attention. I'm more than happy to listen to your questions or comments. So with that said, let's get started. But before we talk about what's special about Haskell, let's first ask the question, why should we really learn something like Haskell? Well, there's a fantastic book called Pragmatic Programmer, and in Pragmatic Programmer, they recommend that we learn a new language every single year. And when they say new language, they're not talking about language very similar to what you already know. Like if you know Java and you're learning C#, that doesn't count. So you have to learn something that's very drastically very different. And the reason they recommend that, you learn a different language, it changes your line of thinking. But to me, one of the reasons I learn a different language is not so I could quit programming in the language I'm programming in and do something completely different, but it really is that when I learn a different language, I can come back and program in the language I program in, but in a very different, better way. In a way, think about this like traveling. If you always lived in one part of the city all through your life, versus if you travel around the world and then you come back, you're going to be thinking very differently when you come back. You're probably going to make changes around you based on what you learned during this trip. And that's actually the idea behind just using a different language. If you're interested in learning functional programming, I cannot think of a better language than Haskell, because Haskell is a pure functional language. But be ready, Haskell is going to hurt you really bad when it comes to the syntax. And the reason it's going to hurt you really bad is because Haskell is bad. It's because we are so used to programming in one way, it becomes really hard to make the switch. I found it extremely hard, and I used Haskell for quite a bit because of that. And then I would push it away, and then a couple of weeks or months later, I would take it up again. I'm like, oh, I cannot handle this. And then about third or fourth time, I realized what the problem was, and I was able to make much progress with it. So given that, what is really Haskell? Well, Haskell is a purely functional language. What does it mean purely? It simply means that it will go all the way to enforce functional style, and that is immutability is preserved every bit of the way. And the default is immutability in Haskell. It also provides functional style in that you can use higher order functions, pass functions around, use function composition and stuff like that very easily, but we'll talk about some of the benefits along the way. But Haskell also is a statically typed language. It is very inappropriate to say Haskell is statically typed like Java. That doesn't even come any close to it, right? So Haskell is truly statically typed, and the static typing is just plain amazing. There are quite a number of seats in the front for people who are in the back. There is seats in the front. It's perfectly safe to sit next to her. She's actually all right. I've known her for a while. She just looks intimidating, but she's actually very friendly once you get to know her. So you can come and speak to her. It's perfectly safe, trust me. Yes. Okay, very good. So it's a completely statically typed language, so we can't really compare this to what Java does. And in a way, you could say, when a language is more statically typed, you would do less typing with your fingers. If a language is not so much statically typed, partially, you would have to type a lot more. And Java has really shown us an example of how poorly static typing could be implemented actually. Because you keep typing the type information so often when it comes to Java, Haskell on the other hand, you really not say as much type information, gets it type a lot. For people in the back, if you're standing, you want to sit, there's a lot of seats in the front. So to come to the front. So let's talk about that with a little bit of examples along the way. It also ensures purity really well to a great extent, and that means you cannot mutate variables along the way. And it clearly separates the pure core from what I call as an impure peripheral. So it gives us a nice purity circle. I'll talk about this also more later. But one of the beauties of this It is very easy to get good performance out of it through optimizations. It is also really useful for proving correctness of code, because with less mutability, it's easy to prove the correctness. But let's warm up to Haskell and work. One of my favorite is called a REPL. A REPL stands for read, evaluate, print loop. And read, evaluate, print loop REPL, if you're programming in languages other than Java, most likely you have either used REPL or you should be using more REPL. Python, for example, has REPL. You got Groovy has REPL. Scala has REPL. Almost any language has a REPL. So REPL is just a shell where you can type in code, immediately it evaluates the code and gives you a response. That's what is the read, evaluate, print, and then keep looping it. So that's what you're seeing with the REPL. And REPL is a great tool for a couple of different reasons. REPL is a great tool to type in a little code, so it can nicely give us a way to experiment with the code. But in the case of Haskell, because Haskell is statically typed, but Haskell is also uses a heavy dose of type inference. When you write Haskell code, it's not that easy to query for the type of an object. Haskell kind of says, why do you care about the type? It's my business, not yours. But REPL is a great place to go in and say, hey Haskell, talk to me, tell me what this type is. So it becomes a little chat to you, so that's a nice way to deal with it as well. So let's take an example here. I'm going to go to the REPL here for Haskell. So I'm going to bring in a REPL. And once I bring in the REPL, what I'm going to do here is, I'm going to simply say hello right here. And that is actually a valid Haskell code, as you can see. So it was happy to run it, and it tells me that it's a collection of characters. That's what it's returning to us. So likewise, you can write a little bit of code, and you can try to see what other things that Haskell can provide for us. And you can also ask Haskell to give you type information as well. For example, if you were to say, oh, say 3 plus 2. Well, in this case, of course, it tells you that 3 plus 2 is 5, and it gives you a little bit of details about it. But after the fact, you can say type of that variable it, and it tells you the same information, so you can go back and query it if you are interested in. So that can give us a little bit of an insight into things. So this is a good way to quickly experiment with some code. But talking about types, Haskell is statically typed. So what does it mean it's statically? Well, it performs quite an amount of type verification at compile time. Now, what is the good thing about type verification compile time? Well, there are a couple of different benefits to it. You can weed out some errors even before the first line of code is executed, right? That definitely is a benefit, because if you can remove some of the errors ahead of time, that definitely is a benefit. Why would you want to postpone those to the runtime? So it performs a really good amount of compile time checking. A lot of different languages do compile time checking, right? So Java does, Scala does, and Haskell also can do quite a bit of compile time checking. However, you don't have to really specify the type for you to really be able to use it. For people who just walked in, there are seats in the front. If you want to walk to the front, you're welcome to do. So for example, let's say a friend comes to your house, or you bring a friend to your house, let's say, and when you introduce the friend, you normally, I'm hoping, don't have to introduce saying, this man is my friend, right? By the looks, you probably know it's a man, right? Okay, there are some people who are not too sure, but mostly. You know, for me, the biggest trouble I have is with little babies, right? I always make this mistake. I would say, oh, he is so cute. And the parents are like, it's not he, it's she. It's like, sorry, I can never get this right. So for adults, it's not a problem. Except it can be quite dangerous, because I was at the airport one day, and I got to tell you, very dangerous person, and I almost went very close to a hug because there was a long hair. I was about to hug when the person turned, and I did not see a beard, and I realized it's actually a lady and not Scout Davis. So I can get very dangerous, right? Looking at the back, you kind of have a type inference, wrong mismatch. But most of the time, you know what the type is. So the point really is that you don't have to say the type. If it can infer the type, that can become very beneficial. And of course, it's strongly typed. What's the difference between static and strong? Strong typing is, it not only knows the type at the compile time, it knows the type at the runtime as well. And that information is available quite easily. There are seats in the front. Please come to the front. There are seats available. You don't have to stand over there, but you're most welcome to stand if you want to. So that's basically what we're doing, is infer the type. So let's take a look at an example here. Suppose we were to say add over here. So I'm going to create a function to add stuff. So what would I do in this case? I would say, let's do this in the REPL itself. So I'm going to say add, let's say A and B equals A plus B. Well, in this particular and he looked at what you're doing with those two values. And what are we doing with those two values? Doing a plus. And it said, what in the world would use a plus? And it looked at its type system and said, oh look, plus is available on number, so it's got to be a number. So it inferred the type as num, as you can see, based on that. So suppose I were to go back here and say, call add with the 2 and 3, it says, sure, I can do that. If I say add with the 2.1 and 3.2, it says I can handle with that as well. But if I call add with the A and, let's say, B, it says, sorry, I can't work with you. So notice how it was able to do static typing without we having to specify the type, right? So this is one of the things I did really wrong when I got into Haskell. I read that Haskell is statically typed, and guess what I was trying to do? Specify the type over and over and over, and I got really tired and I gave up. And then one day I woke up and realized, why do I have to say the type, right? If the language is smart, it can figure it out, and these days I very rarely actually say what the type is, and the language is very happy, right? But the language looks at me and says, kid, you finally know what this is all about, right? So I've been really doing more work than I really need to, and it really figures this out very easily. So that is what we are seeing in this particular case. We don't have to specify that. However, this is another amazing thing with Haskell. Haskell has what's called a polymorphic type. Notice when I created an add method, it said that add A and B are going to be numbers. How did it know that? Based on the fact that I used a plus. But if I say echo A equals A, now what does the silly echo method do? You tell it something, it tells it back to you. Well, what do you think can be the type in this case? It could be a string. Anything else? Number? Anything else? Anything. It doesn't matter what the type is. So what is the type? Well, it could be anything. But Haskell says, yeah, it can be anything, but it's got to be something. That is called polymorphic type. Polymorphic type simply means here is a type, but I can figure out what the type is, but it can be any type, so it is willing to really give you a flexibility of. I don't know if you notice this. Watch this carefully. When I define add actually here as a function, notice in this case it said add : num. So the syntax here is add is the name of the function, : num is actually what this guy is going to return for you in this particular case. But if I say let echo A equals A, notice in this case it says T dash T. What in the world is T? I want you to pay close attention here. Num starts with the uppercase letter N. Types in Haskell starts with uppercase letter. T, of course, doesn't start with uppercase. It's a lowercase, so that means it's not really a type. It's a polymorphic type, right? So it means let T be a type, right? Rather than saying that's a very specific type that you're dealing with at this point. So what can you use for this? You can say echo with a 1, I can say echo with a high, I can use echo with the 2.2 and so on, but notice every single time it is using a different type. Now what is the thing that very closely comes to in Java to this concept? That's right, generics. But you know how world apart they are, right? Generics doesn't even come close to it. Generics is this is what generics would have been if we didn't mess it up, right? So that's what this is kind of the polymorphic type. This is what true generics should really be when it was done properly. That's how it should feel like. Great. So we kind of relate to what this is about. Let's talk about collections for a minute. I want to be able to create a collection.
Well, you know how you create collections in Java, right? You say list and then you say new array list and then you start putting add and add and add, or you say arrays dot and then you start putting, you can do all of that, right? So what I'm going to do here is, I'm going to say in this case, create a main for a minute. And I'm going to say let list, or let's call it nums equals, and I'm going to simply say here are the values I want to work with. And when I'm done with it, I want to simply display the values in this collection. So it was pretty easy, wasn't it? But this nums actually is creating a list. In Haskell, collections are totally immutable. So you cannot create a collection and then go back and change that collection. You're not allowed to do this. You cannot change a collection, so it's pretty safe. You can share it, and you cannot really remove it. Now you may say, oh my gosh, if a collection is really immutable, then that will result in a poor performance. We'll come back to that in just a minute. So now we have this, but here's the cuteness. Rather than going through that much effort, I can simply do this. And I can simply say 1 to 6 dot dot. It's like, sure, I can create that for you. That's pretty convenient, isn't it? But even better, you can say, I want 1, 3, up to 10. This is like language is learning from what you're saying, right? It says I'll do 1, 3. Oh, the gap between those two is 2. Next is 5, next is 7, and begins to kind of go through and learn from it. That becomes pretty powerful, as you can see. It begins to extend that very nicely. And so with that, you can start doing other things as well. For example, if you say 1, 4, it knows to spread that out properly. So we have a collection that we can create very easily, as we can see. However, let's say we are interested in working with this, but what if I want to take 2 collections and bring those 2 collections together? Well, if I want to bring those 2 collections together, what would I do? Well, that's a list operation. We can do concatenation operations. We can also do a concatenation. But what does that really mean? Well, remember, a list is totally immutable. So which means you cannot change a list once you create it. Well, that means it should be poor in performance if you have to make a change after all. Because you cannot change it, you got to make a full copy, right? Well, not really. So let's take one hypothetical example here. So here is a wonderful set of people on the front row, and that, let's say, is a list for us. Well, that list is immutable, right? Look at the way they're not even moving. They're all kind of stuck over there. That's immutable list. And if I go to them and say, I change you, they're going to say, of course not. Take a hike. You cannot change it. Well, that's an immutable list. One naive way to make a change to the list, which is immutable, is to make a full copy of the list. So 4 elements, but I want 5 elements. What am I going to do? I'm going to make a copy of a new list with 1 new element and all the 5 elements. What is the order of the performance? It's an order of n, isn't it? If there are n elements, it's going to take an order of n operation, not very efficient at all. However, there is something else we can do. Because that list is immutable, there is one big advantage. What is that? You can share it. Because if something is immutable, it is very safe to share it. Would you agree with that? Right? Because it's not going to change, it's very safe to share. So what I'm going to do is, I'm sorry, with all respect, I'm not going to ask for permission here. I'm not going to walk over here, stand here and point to and say, I am beginning of the list. I don't care what Puneet thinks. I don't care, sorry. He could say, I don't want you to be in the list. Well, he has no choice. Now you can come to me and say, hey, how many people are on your list? I'll probably say there are 5 people in my list, right? And I quietly shared the 4 people in there, and there's nothing they can do about it. Make sense? So that's because that is a suitable list, and I can add myself to the head of the list, right? And no matter how hard he tries, Puneet has no luck in this matter, right? So he feels like he's at home, right? Just feels that way. Yeah, he has no choice at home too. Okay, so that's an example of how I can just add this to the list very easily. But that's a different case if I want to add to the end of the list. Because if I want to add to the end of the list, what's going to happen? Well, he has to accommodate me as the last element. He's got to refer to it, and he says, well, sorry, I won't do that to you. So as a result, to add to the end. What does it take to add to the end? I got to make a full copy to the end. But to add to the beginning is an order of constant operation. Am I making sense? So mostly functional programming languages work through adding to the head rather than adding to the end. There is also another data structure called tries, T-R-I-E-S, which also gives you very efficiency. Well, languages like Clojure and Scala use that for vector implementation that can make constant time copying without really much overhead at all, which is really, really powerful for large data structures. So given this, what I'm going to do here is I'm going to simply say head nums, and notice it gave me the first element in the collection. Likewise, you could say tail, and that gives me everything other than the head. So tail and head are very common operations that you use in these languages for that reason, because I can take the head, I can take the tail, I can introduce a new element into this, and so on. We can work through it very nicely. So that is an example of how we can work with this tail and head. I could also say init, and that is everything except the last element in here. I could also say last, and that's everything, only the last element, and it kind of removes everything else that was in there. So you can do these kinds of operations very easily. However, you can also do, let's say nums1, which is going to be 1 to 5, and you could say nums2, for example, equals, let's say, in this case, 6 to, let's say, 10. And now I can say here is my nums1 that I want to print, and likewise here is my nums2. I want to print that also. But given this, I could also say, example here, print, and this could be nums1 plus nums2, but it doesn't modify either one of those collections. So if you were to come back and print those two collections after the operation, you will notice that they are still intact, right? So that's an example of how you can start concatenating things. Likewise, you can use a colon to put something in the beginning. So we saw the head, we saw the tail, but some other very powerful operations we can actually perform. One such operation is called the take operation. So what does a take operation really do? A take says, well, I want to take 3 elements from nums1, and you can see in this case it only gave you the first 3 elements. So this is like a head, but it gives you a little bit more than just the head. You can also say drop 3, and in that case it drops the first 3 and gives you the remaining elements. These are very powerful operations, and you're going to see some operations like this available in languages like Java also. Some of them are already available, some of them eventually will show up, and if you look at languages like Scala, they provide quite a number of these already. So that's an example of how you can do a drop or a take methods. But not only can you do those kinds of methods, but you can take this to the next level. You can do an elem. Well, it's a little misleading. Elem doesn't tell you what element at that index. It is a Boolean check. Does it exist or not? And just tells you whether an element exists. But let's talk about filtering for a minute. This is one of the things I really like about in Haskell. So I want to say a filter, and what do I want to filter? Even from num1. And let's make this a little bit bigger so it's easier to see what's going on. So I want to say 1 to 10, and in this case you can see that in this particular case I can ask for all the even values. This is pretty amazing because you can call the filter, but to it you're passing yet another function, which is the even function. That makes the function a higher order function. So filter is accepting another function as a parameter followed by an object collection in this case, and it says I'm going to pull that in and I'm going to run through that, so it gives us all the even numbers from the collection very easily. Not only can we do this, we can also do something like an odd value, for instance, and you can see that it gives you only the odd values, or you can even say is greater than 3, for example, where is greater than 3 is going to take a number, and it says number is greater than 3, and that gives you only numbers greater than 3. You can pass own functions to it as well. Now, this is something you can do in Java also today fairly effectively, right? So you can start benefiting from some of those very nicely. So as a quick example, let's say for a minute, I go back here to Java code, let's say, and I'm going to say here is my, let's say I have a list of values to work with. So I got these numbers, and I can say output numbers dot, let's say, stream, and I'm going to create a stream object, and then I'm going to say dot filter, and given an element, give me an element mod 2 equal to 0, and then for each of those system dot out print line, and I want to print those values. You can see a very similar thing we're doing here in Java, right? So filter is an higher order function. It is taking a function which is going to do the even, and notice how to the for each method we are passing the print line function, much like how we pass the even function. The syntax looks a little bit more noisy here, but the concept is pretty much the same. You're passing a function to this other function, and you're able to carry those kinds of concepts around very nicely. So you can see how that kind of shines here in Java as well. And so that is one of the things we start thinking about. So we use that, and we also use our own function as well. This is not available in Java at this time, unfortunately, but other languages like Scala have it, which is take while and drop while. Well, when I say this is not available in Java, I should be very careful how I say it. It's not available in the JDK. If you're programming reactive systems, I got a talk on reactive programming tomorrow, and I'll be using RxJava in there, and RxJava is a library created by Netflix, and they have this exact method called take while and drop skip. Actually, they call it skip while rather than calling it drop while, but it's pretty much a very similar concept. And when you get into these things, when I looked at take while and skip while, I didn't have to think, because I've seen it already in Haskell. I'm like, oh sweet, these guys have this function, thanks, right? So that's one of the benefits you begin to get by learning these things. You are preparing for having those things in either other libraries that you will come through, or you'll be ready for it when the language improves. That is one of the biggest benefits you get, is that doesn't become a strange concept at the time you look at it, because you have seen it already a few times. That can make a pretty easy transition. So when you look at reactive programming, you're going to get a stream of data coming in, and you're going to say, I want to take some values in the stream, or I want to skip some values in the stream. It gives you the ability to do that. So let's quickly take a look at what this take while and drop while is going to do. The take while and drop while, for example, in this case I can say take while, and what am I interested in taking while? I'm going to say even nums1. It says there is an empty y. It says take while the numbers are even. So what about 1? 1 is already not even. It says bye, I'm done, and it goes home. On the other hand, if I say take while odd, well, you can see in this case it hit 1. Hey, 1 is odd, I took it. It comes to 2 and says, oh, 2 is not odd, I'm not going to take any more, right? So keep taking while this is true. You saw take earlier, but take worked only with a number. Take while is more logical. It examines the values to make that decision. Likewise, if I say drop while, and I'm going to say even. What does that mean? While you see even numbers keep dropping. Well, in this case, it went through 1, and it says, oh, this is already not even, so I can't drop it anymore. I got to plow through entirely, right? It went through. But on the other hand, if I say drop while odd, you can see in this case it dropped 1 because it's odd, and then now that it dropped the 1, now it's got to start picking up, right? It takes a little bit of thinking, but you can get the point very quickly. So we saw the list, and we talked about how immutable it is, all those nice things. I want to quickly mention about tuples. Tuples are really, really cute. I love tuples for 2 reasons. One, tuples are so short and nice, and the other reason I really like tuples is most people pronounce it really badly. They say tuples, right? Well, no, it's not tuples, it's tuple actually, but it's always funny to hear that. So, but tuples are really cute. A tuple basically, say tuple like it's a couple, right? You don't say tuples, right? So it's very similar to that. So it's a tuple. So tuple basically is just a collection of data, much like a list, but in this case, of course, it doesn't have any particular requirement on the types. It could be a varied type or a mixed type if you want it to be. It's very easy to create a tuple. It's very lightweight. The syntax of tuples syntax for tuples in Haskell and Scala are pretty similar. Scala was greatly inspired by Haskell. That is one thing you will see time and again. Languages and libraries are often influenced by other languages and libraries. So once you learn languages, you're then saying, oh, one is like that, and you pick it up much more quickly, it becomes a lot more easier to work with. So as a result, let's go ahead and take a look at this quite quickly as an example. So I'm going to go back here and say in this example, I'm going to say over here, let's say let pair equals, and I'm going to say this is Tom, and then I'm going to say this is Jerry, right? So I'm interested in printing it out. I'm going to say print the pair, and you can see that in this case it printed that. Now this reminds me of one experience. I can't make this up. This actually truly happened. I made a phone call to a company. I wanted some service, and I made the phone call. Somebody picked up the phone. I was supposed to talk to somebody, and somebody picked up the phone, and I said hello, and I said, "Can I speak to Tom, please?" Without missing a beat, the guy said, "Well, Tom is not here, but I'm Jerry. May I help you?" I hung up the phone, right? I couldn't believe this. So that's Tom and Jerry. So what do I want to do? I'm going to say here is the first, and I want only Tom in this case, right? So first gives you the first one, which is the Tom. And of course, I'm going to say second, and that gives me the second object. So that gives you an idea how we can start accessing the element in a tuple. Java doesn't have a tuple. This is kind of breaks my heart. I hope have it eventually, but of course you can use the Apache Commons library, and there's a pair object available in it, so that may come close. Java also has an entry object for a hash map entry. You could probably potentially use that as well, so you can start using some of these methods. But I want to shift attention to this beautiful thing. How does this help? Well, once you understand this, you would rethink the way you design your own libraries and API. Look at the word statement and look at the word expression. Now, what is a statement? A statement is really evil, right? What does a statement say? You go to a statement and say, "Hey, statement, can you do some work for me?" And the statement says, "Oh, of course, yes." You say, "Thank you, statement, do this work for me." Statement says, "Yes, I'm done." Okay, what did you do? And what does a statement do? Tell you. It says, "I won't tell you," right? A statement will only do the work. It will never give you back a result. And isn't that terrible, right? You call a statement, it does some work, and says, "If you want, go back and get it over there," right? And very rude. Expression, on the other hand, what does it say? It does the work and nicely returns the result to you, right? How polite of it, right? Very nice. It does the work and says, "Here you go, this is the result." So what do you know from a statement? The only way a statement can be of any use is if it performs what? Mutability, right? If it only performs mutability. There is no way to use a statement without having mutation. Well, guess what? A pure functional language does not permit mutability. So what can we infer from that? There's no statements. Isn't that wonderful? A functional programming language, a true functional programming language, has no statements. Everything is an expression in that language. What is the benefit? The benefit is you can nicely compose. Call an expression, get a result, call another expression on it, get the result, and you can nicely compose from it. So let's take a look at an example of that and see how that feels like. Well, if I'm writing Java code, and if you say if, what do you call that? What do you say? It's a if what? It's an if statement, right? Why do you say it's an if statement? Because you call if, and what does it do? It changes some memory and says, get it, right? So you cannot call if and take a result from if. What do you get if you get a result from if? A compilation error, right? That's what you get, right? You get a compilation error, right? Java looks at it and says, "You're new around here?" Right? So that's what Java says, right? It kind of looks at you and says, "Are you new here? Don't you know I don't give you back results," right? That's how Java looks at you, right? You should actually have a picture of Java compiler looking at you when you write code. That would be a nice way to write Java code, right? You're typing code and the face kind of changes like, "What are you doing here?" So that's what Java is going to say. Right? What are you doing? You're trying to get a result from me, huh? I'm a statement. Well, wouldn't it be nice if you can actually get a result from a statement? So notice what I'm sorry, from if expression. So let's give it a try here. So I'm going to say, can I vote age equals, if age is greater than 17, then please vote. Is 18 voting age here still? Yep, so you can vote. Else what? Well, else, go home kid, right? So we can write it that way. So in that case, what we could do is we can say print, can I vote 13? And notice what it tells us, go home kid. Or I can say print, can I vote 23, right? And you can see that in this case, it says please vote. So you can see how the if statement, if expression, depending on which route you took, you are able to use that. So that is an example of expressions rather than being statements. Now you may say, you could do this also in Java by putting a return statement, a return expression, but that's only possible if it's in a return, whereas here you could take the value and do more things with it. It becomes a nice composition available for you. So what we learned here is that a pure functional language will only have expressions, no statements. How does that help us do our work? Well, from tomorrow, as you start defining your own APIs, your own functions, think about it. To go a little easy on void functions, void methods, right? Because the more void you create, what do you get? You get more void, right? So you don't want really as many voids because they become statements. Instead, be nice, do some work, return a result. Then what happens? We can nicely compose methods on it, right? And then we can apply the compose method pattern. You can create more fluent interface, and you can get influenced by that kind of writing. Where when you go back and program in Java, you can say, hey, that's a pretty interesting stuff. What if I turn into more expressions than statements for the code I'm going to write? We start writing code somewhat differently than what we used to, and that's when we begin to benefit from some of these ideas. So, excellent. What about functions? I want to define a function. Well, defining a function we just did. Notice can I vote is a function we just defined. Let's go ahead and create one more. Greet name equals, and I'm going to say greetings over here, plus name. And now I'm going to say main, and I'm going to call greet over here. And greet, let's go ahead and call, send a string, earthlings, right? So in this case, of course, when I run this little code, you can see in this particular case, I'm going to go ahead and call this and concatenate it. So you can see that it's going to say greetings, earthlings. So you can see how we can call the greet function. However, the greet function has one special benefit here. The greet function is a pure function. So what's a pure function? A pure function is a function that does not have any side effects. So a side effect is where you call the function and it changes things around it, right? So you call a function, and then what happens? After you call the function, you say, hey, thanks, here's the result, and you look around and it's left a mess behind it, right? And you got to say, oh, it corrupted that data, it corrupted that memory, and it creates a mess. So what will happen if you call functions and they have side effects? You're going to be really wary of calling it, right? You're like, let me be sure, and you clean up everything. This is like you invite one little, niece or nephew, you know what I'm talking about, right? And your niece or nephew says, your sister or brother says, I'm going to come to your house on Sunday. What do? You lock everything down. Because niece or nephew comes over, it's a riot in the house. I got one brat like that. He's the cutest man on earth, I'll tell you that. But he comes, we have to safeguard everything, right? We call the national army to defend us when he comes to our house. So that's kind of like that, right? You just call in, it's like, what do you do? And then it's like, oh, about 2 weeks later, we'll be still discovering damages he has done to the house, right? It's kind of like that, but it's really cute, but it's fun, but not always. Okay, so the point really is that you don't want functions to have side effects because it becomes really error-prone, buggy, hard to maintain. But what does a pure function do? You give it a data, it does some work, gives you a result, and it says, I didn't do any damages, right? Here's a result for you. It's easy to test a function which is pure, right? And as long as you keep sending the same input, it gives the same output, and that's beautiful. It's easy to test it as well. It's easy to reason with a method like that, with a function like that, because it's taking an input, giving you a result, you can go through and say, yep, that makes sense, that's how it should work. Nothing is really changing rapidly along the way. It becomes easy to understand, easy to explain, easy to work with, easy to test, and there are some other benefits that this gives you. So in Haskell, functions are always pure unless you say otherwise. In the case of Java, functions are always impure unless you say otherwise, right? So you can see the saved default versus the unsaved defaults. So this is something where it falls towards purity. As a result, the compiler can perform quite a number of optimizations very nicely. But let's talk about the true nature of functions in Haskell. This one was mind-blowing for me. So let's understand this with a little example here. So I'm going to create a function here, and the function I'm going to create is called echo A is equal to A. Now take a close look at this particular function. How many parameters does this function take? 1. How many results does it return? 1. How do you know? You know it because of this, right? You see that? It says take a T and return a T. So good? Yeah. Excellent. Now, I'm going to say let add AB equals A plus B. How many parameters does this function take? I heard 2, I heard 1. Who cannot count here? Somebody said 1. Who's that? Somebody said 1, didn't they? Who said 1? There you go. And you are correct. That is absolutely correct. Right? How is it? Well, that's the beauty of Haskell. Haskell says this is called currying. Oh, by the way, have you ever wondered why Haskell is called Haskell? Haskell created it. Well, so I just used another word just now, right? I said currying. What am I talking about? I'm not talking about that wonderful spicy dish that we all enjoy, right? Yum. No, that's not the curry I'm talking about, right? This is even a better curry. Imagine how your life gets celebrated. Isn't that wonderful? A guy named Haskell Curry, a logician, and he didn't create the language, nor did he create the word currying either. He did a lot of work in the field of logic and calculus and category theory, and people who came after him said, hey, that's such a wonderful job, and so they decided to give the concept of currying to his name, and they also named a language after him. What a great way to live a life, right? You get a language named and feature named after you. I couldn't ask for anything more. That's how Haskell Curry, his name kind of got fit, and language versus the feature. So what is currying? Well, the idea behind currying is this. If a function takes, let's say, one value, it's easy to think about this. Let's say a function takes one parameter. Imagine this function is a Boolean, just for a minute, all right? It's a Boolean input. What are the different possible values you could ever send to it? 2, right? A 0 or a 1. Fair enough? Now imagine I got 2 input. And again, keep this in binary. How many can you send to this? 4. Which of these 2 is easier to test? First one or the second one? First one, absolutely, right? Because you don't have 2 values to worry about. In this case, you got 4 values, different combinations. Now, suppose a function takes 2 input. Well, what I could do is the following, right? I could say, well, you got a function that's taking 2 input. So let's say the function is, let's say for a minute, writing pseudocode foo A and B. What I can do instead is, I can say, well, I'll call foo 1, and I will only send a value of A. And this will say, oh, give me a A, but I don't have the value of B yet. Then I can say, here's a function foo2, which accepts a value B, and in turn calls the function, the foo1A, with the second value. So internally it can fill in the gaps and say, I'll cache one value for you, and you only give me 1, right? So in other words, you take a function that takes 2 parameters, and you rewrite it as a function that only takes 1 parameter, and what do you want to return? This is where it gets a little tricky. So let's say you have a function foo that takes, let's actually write the code in a way we understand it. Let's say int foo, int a comma int b. This definitely is not Haskell. I'm writing a pseudocode, right? So this is my function. What is the return type of foo in this case? An integer. So this would be something like return, right? It will be return some value which is an integer. Instead I'm going to say foo1 int b. What do you think it's going to return? It's going to return a function which will take a. So, and then in this, I will use a and b to create the result, right? So in other words, foo1 is a function that takes one parameter and returns a function that in turn takes the second parameter, right? So you took a function that takes two parameters and you convert it to a function that takes one parameter. Now this becomes easy for reasoning with functions. So if you want to prove correctness of functions, that becomes a lot easier. This also becomes easier from the testability point of view as well. So if you go back to Haskell here and notice this carefully, you run this, look at that. It says, I'm going to take one parameter a and I'm going to return. What am I going to return? Here's the way you read this. If you really want to read this and understand, read this like this, as that. Now what are you saying? Given an input a, I'm going to return a function which will take an input a and return an output a. Remember, a is a type in this case, right? So given a function that takes a type, I'm going to return to you a function that takes a type and returns another type. So in other words, you took a function that takes two parameters, and as you rightly pointed out, it actually becomes a function that takes one parameter. Making sense? Now you can see how this kind of continues further. Suppose I were to write something like this. If I say let add 3 equals a, b, c equals a plus b plus c, you can see what that's going to be. Well, in this particular case, oops, wrong place. So if I say a plus b plus c, you can see that it's going to become further down, right? So it becomes all these kind of chain of functions calls, and that is the really true nature of how the functions are. Well, this leads us to partially applied functions, which in my opinion are wicked cool. So let's say we have a function called minus, where it takes a and b and returns a minus b. I can then say main, let's say equal to, and I'm going to say in this case, well, print minus, let's say 2 and 3, and clearly that's a minus 1. But instead I'm going to say, in this case, let minus 2 equals minus 2. So I just created this, and then I'm going to say print minus 2, and I'm going to create like that. So minus 2, and I specified 3. Now what happened? This is called a partially applied function. The word application means you are invoking it. Here you're not fully invoking it, you're partially invoking it. This is like you're talking to somebody, I need two things, you say, hey, hold on to this, I'll get you the other one, right? So you're giving one parameter. It says, oh, now that you gave me one parameter, I'll give you a function that's waiting for the other parameter, right? So this is kind of what is internally happening to create the partially applied functions. This becomes very useful because you can cache one parameter and they can pass it around and they can pass the other parameter for you, gives you quite an interesting flexibility on your hand. Likewise, you can also do the opposite, where you can pass the other parameter. In this case, it became the second one instead of the first one. You can work with that also. But one of the charming features is the lazy evaluation, and we have to talk about laziness. Now, what does lazy evaluation really mean in this case? I want you to quickly take a look at one example here. Suppose you did something like this. Public, let's say static int compute, and here I'm going to say number, and I'm going to output this particular call, and I'm going to say return number, let's say. And now I'm going to do the following. I'm going to say here int value equals 4 if value is greater than 5 and compute, let's say 4 is equal to 4, then I'm going to say result, right? I'm going to run this code. What can you tell me about the call to compute? It will work or not? Will it call it? It will not call it, right? Why won't it call call it? Because it's a short circuit. You agree with that, right? So else, I'm going to say no result. So you can see in this case, it never called it. Happy? I'm going to change this a little bit. I'm going to say v equals 4, int v equals compute 4. What do you think now? Will it call it? Let me ask you a different question. Do you think it should call it? No. You feel cheated, right? You go to Java and say, give me my money back, right? Don't you think? You never use the variable value, right? If Java was really smart, it would say, I don't need to do this stuff, because you never are going to use the variable v, right? Am I making sense? That's the way real short circuiting should work, right? Well, let's see how Haskell does it. So here in Haskell, I'm going to say add ab equals a plus b, right? And then I'm going to say here, evaluate value equals value, happy? Main, and I'm going to say print, evaluate, add, let's say 1 and 2. So run this code, it's 3, right? Great. Let's do something else. Let's bring up the repo. I'm going to load this file, sample.haskell hs. I'm going to put a breakpoint on line number 1 and column number 16. That's where the breakpoint is going to be. So right there is 16. Then I call main, and when I call main, it's breaking, isn't it? Then I say continue, and it says, okay, I'll continue and give you the result of 3. Makes sense, right? Did it stop in the function? Absolutely, it did. Now let's get back here. I'm going to say, give me a value, but I'm going to return a 42. Now look at this closely. This is called, in Java we use what's called applicative order. In Haskell we use what's called a normal order. The normal word is actually not normal at all in this context. But Haskell is extremely wicked smart. Here you're saying, well, normally what do you do in Java? You call a function, you put a parenthesis, a parameter, what does it do? Evaluate it now. That's evaluation. And then you call the function, and the function doesn't even care about the value. You did all that extra work, right? Haskell is very smart. You went to this and said, hey, print line, evaluate, add 1, 2. Haskell says, oh, you're calling add. I'll come back to you. Hang on. Oh, you want to call evaluate. I'll come back to you. Hang on. Oh, you want to print. Of course, I got to have a result to print. Hey, evaluate. It goes here. Evaluate. I got a value for you. I haven't evaluated it yet. It says return 42. Haskell is like, phew, I didn't do that work. So it never runs add. It is lazy, keeps postponing it. Well, to really see this happen, notice in this case I run the code, it says 42, but if I go back here and I load the code one more time, put a breakpoint one more time, run main, it did not stop in that function at all. Why? Because it said, poof, I don't have to run add because nobody uses the result for it. That is laziness baked into the language, as you can see. Pretty darn powerful. Well, you can take this further. You can kind of relate to this very quickly, right? You cannot apply lazy evaluation if your functions are not pure. Would you agree? So let me ask you one question. In Java, you have a class, some class, call it my class. You say, literally, new my class, parenthesis, open, close, semicolon. You never assign this to a variable. Will Java create an object, run the constructor, and leave the object for garbage collection? Or will Java quietly skip it over? What do you think? It will create it. Why? Because a constructor can have mutability. Constructor side effect. You see that really, right? If constructor, you promised, I promise, I will never change anything in the constructor. What will Java say? Cool. I don't have to do that garbage. So you see the fundamental philosophy behind the language? A language built on mutability has to do more work. A language built on immutability can be very lazy. Which one is better? Absolutely. Be bold, say it. Remember when you were in school You really worked very hard for an exam, you kept studying, this other guy never studied, and you said, what a loser, right? And then on exam day you wake up and say, I'm all prepared, and it pours rain, cats and dogs, and the entire district school is closed. Who is smart here? Right? That dude says, oh, you know what? Losers, right? Well, okay, maybe not that extreme, right? But that's efficiency baked in, isn't it? Absolutely, you want that. So, given this, how do we work through it? Well, you can use recursions because of purity again. You can use this very nicely. So, for example, factorial, or actually in this case, yeah, factorial, and I want to find a factorial of a number. Well, here's the beauty. I can say 0 equals 1, and factorial of n equals n times factorial of n minus 1. And then I'm going to say, in this case, equal to, print factorial of, let's say, 5, if you will. Well, take a look at this for a minute. This is a bit weird, isn't it? You defined 2 entry points to this function. One with the value 0, and another with the value n, and it picks and chooses whichever it wants to. So that again changes the way you think about it in terms of how you can call these functions. You can also pass guard statements to it also. But that brings us to lambdas. You can write a lambda very easily, but very rarely do you actually write a lambda in Haskell. And this is kind of weird, right? It's a strongly typed language. You don't really say the type most of the time. It's a functional language, but you don't have to really create lambda as much, right? So these are like very cogent interfaces. You can take any function, you can pass it down to it if you want to. Likewise, you can use function compositions. Here's an example of that. You can say, here is a function to write it. You can see there's a problem with this code. The problem in this code is, if you notice, you got to read it right to left. Most of us are not good at reading right to left, right? Most of us are comfortable reading left to right. So thankfully, there's a notation for that. You can say, go this way, dot, 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 up to this point. It can become a little easier to read. But anyways, purity and immutability can give us a great deal of benefit. But realistically speaking, can you think of an application where it is absolutely pure? Nothing ever changes. Actually, I can show you one example of a code which is absolutely pure, where nothing ever changes. Are you interested in seeing it? So here it is. Right? It's absolutely pure. What does it do? Nothing. Right? That's only a small point though, right? So in reality, we have to have mutability. Without mutability, we cannot have anything really working, right? If you really want total immutability, this is like some people at work. They show up to work every day, nothing comes out of them. Right? You never get any result from them, right? You always wonder. You show up every day, what have you created, right? So that's kind of, and they can say, pure, right? No, that's not the kind of purity you want. So at the end of the day, you do have to create a side effect somewhere. So think of this as a circle of purity where nothing changes. You send an input, you get an output, and then come with a very thin layer of impurity around it. And that impurity layer is where you perform the side effect. Well, this is called a monadic sequence in Haskell. Now, the idea really here is you cannot just walk to any particular function and say, I want to cause side effect. They won't allow you to do that. You got to specifically mark a method saying this can cause side effect. If you don't mark it, you cannot do it. So to accommodate this, here is an example of a code which performs or allows impurity for us. Let's quickly take a look at one example here. So here's my first impurity example I'm going to use. And this code says, I'm going to call a greet function, but I'm going to say this greet with a do. Do simply says do in sequence, meaning don't optimize it, I want a particular order. What is your name? You're reading the name and then you're printing it. If it was pure, it could rearrange these. That's called referential transparency. And you're like, no, don't rearrange it. Run them in that order. Well, Haskell, you have to tell it to run code in order. This is mind-blowing. In Java, it'll always run in order. Haskell says, I'll just let them toss, and they all can float around. I can rearrange them because they're all pure. It doesn't matter which order I perform them. Well, it's impure. You're saying, hang on, slow down, Haskell. This one is impure. Could you please go through them in sequence? So you have to tell Haskell to do things sequentially. In other languages like Java, you got to beg with it to do it in parallel, right? So the default Haskell is go ahead and toss it around and optimize it. So in this example, it's a different way of writing it. You call this function, and notice you are chaining that output to the next function, and you are chaining that forward. That's just another syntax for it. But what if you want to read a file and get a value out of it? Well, if you want to read a file and get a value out of it, you got to do a little bit more impure operation, and here is an example of that. You're saying read stuff. Notice you're putting do again in this case. If you don't put do, it gets angry because it says you cannot perform any impurity. Reading a file is an impure operation, right? Because you run it once, you got one output, you change the file, run it again, you get a different output. So that's impurity. Then you say return. Return doesn't mean return like in Java. Return here says take this result and wrap it into an impure operation and send it so that these two guys can sequence each other. So you're telling the Java compiler, Haskell compiler, don't do optimization here, and you are putting a sequence through it. And then again you're saying, I want to read the file, put the file content here, and then I'm going to, of course, display that's the content of my etc. host file. So that gives you an idea about how you can force through impurity in a language which is otherwise totally pure, which is the flip of what we do. In Java, it's impure, and you got to work really hard to make it pure. In Haskell, it's pure, and you got to put extra effort to make it impure. So to summarize what we talked about, learning this really gives the ability for us to think very differently. And there are two benefits to this. One, as we go back to programming languages, it becomes easier for us to rethink the way we program. And the second benefit is, as we start playing with language features as they evolve, it becomes easy to say, oh, I'm not a stranger to that. I've seen this one before. I can adapt to it much more easily. It shortens our learning curve as well. I hope you found that useful. Thank you.